Okay. Today we are going to start to discrete Fourier transform. Okay? Can you close the door, please? It's our topic for today. Okay? And so, up to now, we have dealt with continuous Fourier transform. Like this one. We have the F, big F in here. JW is the imaginary part of the R system. We don't have the real part in this case because the frequency only contains the imaginary part. Just remember that. And so we have the minus infinity to infinity integral in here, just like this one. And then we can put into the what the continuous function in here, and then we can combine with the what the E over minus JWT dt. Okay? This is our basic condition in here. This is the convolution part. The image for the what? The frequency. Okay? And this is the R input signal. And so the simple convolutional integral gives us to what? To this relation. Imaginary and the real one, right? And so we can generate to what? To time dependent signal in here, the XC. And so we can gives the what? The frequency pattern in here, just like this one. And so this is the pi, this is the 2 pi, and so this can be created with the what? The I over IT, E over IT equals to minus 1. Okay? And so if we convolve this pattern with any input signal, and then we can get to what? The amplitude or the magnitude of input signal. But in terms of the what? The frequency one. And so independent of the time. This is important. This we should use the Fourier transform in order to what? In order to get the frequency pattern, not the time dependent one. And also if we have the time dependent signal, and so we can go to the what? The infinity. And so we cannot measure or evaluate the signal property with the what? With the t goes to infinity. But in the frequency domain, we can know that we can evaluate the signal based on the frequency pattern, because we don't need to go to the infinity in the frequency, right? And so just remember, we can create the example in here, just like this one. The solve ft is equals to the what? The cosine 2pft using the what? The continuous Fourier transform. Okay? And so we can drive the solution as the ft is equals to the what? This one. F w is equals to the minus infinity to infinity value, and so the ft I 2 pi I w t, and so we can write to what? Minus infinity to infinity value cosinus 2 pi ft times e minus 2 pi I w t. This w is the frequency f, not the angular one. Okay? 2 pi w is the angular one. Okay? So we need to solve this equation in terms of the what? In terms of the exponential terms, the e number, because if we have the cosinus signal, just like this one, we can write this signal in terms of the what? The E over I 2pft plus E minus I p 2ft divided by 2, right? In order to solve this integral, we should know that everything must be represented with the what? With the I term, exponential term in here. And then the integral is easy to be solved, okay? And so, yes. And so, we have the fw in here, just like this one, 1 divided by 2, or these terms in here. We have two parts. One part, the another part can be given in here, and so integral minus infinity to infinity values I over e to pi f minus w t dt, and plus minus infinity to infinity value e over I to pi f w t dt. So we have the one term in here, but this is a special pattern in here. If we don't use the what, the f in here, this is turns into the what? Into the Dirac delta function. But if we have these things and using the shifting property, this can be represented with the what? With the Dirac delta function, but with basic difference. W minus f. F is the specific frequency in here, which is given in the what? In the input signal, right? And so this is also what? This is the plus term in here, just like this one. And so W plus F can be written in here. And so the final integral, which is given us to the what? 1 divided by 2. And so Dirac delta function WF plus Dirac delta function W plus F, which is equals to the what? Dirac delta W minus F plus Dirac delta W plus F divided by 2. Okay? And so this is the what? This is the Fourier transform. And so what's the meaning of the output signal in here? Just see that. If we have this kind of information, and then we can say that we have the one value in here in the graph, right? We can draw the what? The magnitude and f graph in here, right? This is the frequency. This is the magnitude. And so what this equation tells us about itself, just see that. We should know that the Dirac delta function creates the what? Creates the one or the infinite signal, right? Up to the what? Infinity in the magnitude values. And also we have this signal, and so beside from the W minus F, or the W is not equal to the F, and so this yields us the 0 value, right? And so we can easily write that. If we have this pattern, this is the W, so F and minus F, we have two peaks, just like this one, right? And so this is the cosinus signal, which is a uniform signal, periodic signal in here. For example, F can be yielded with the what? With the 5 or 10 hertz, and then we can give us to the what? To the Dirac delta function in the frequency domain, which means that is the f is equals to the 10, we can say that the input signal possessed with the what? With the 10 hertz values, right? This is simple. This is the meaning of the Dirac delta function in the frequency patterns of the what? The signal processing. Okay? Any question? So, but this is the continuous one. This one is continuous. So the original signal ft can be used like the what fj times w, which is equal to the minus infinity to infinity value ft e over j w t dt. And so this is the continuous. But what about we are using the sampling in here in the discrete domain, right? It's important because in a real life application we only have the what, the discrete signal, and so we need to rewrite this equation or this integral in terms of the what, the impulse responses or the Dirac delta function applied on this signal, right? And so at every impulse we have fk. K is the index of the R system. For to what? fjw, and so 0, because we don't have the what? The negative time in here, because it's the real time, right? It always starts with the what? With the 0 value. And so we have the minus n minus 1 times t. T is a sampling period. N is a sampling number. For example, 1000 data is sampled from the signal with the what? Based on the 1 milliseconds. Okay? And so this integral can be written just like this one by using the what? Applying on the what? The impulse response in here. Okay? And so the ft times e minus jwt dt can be written in here. And so if at we apply to what? To impulse response, and so at instant values of this integral can be obtained, right? Just remember that if we take or if we apply the any system or the any transfer function, any S domain or Laplace domain function, if we apply the impulse, and then we can get that, or the in correct terms, that if we apply the Dirac delta function, and so we get the instant value of this signal. And so this integral can be written just like this one, f0 times e minus j0, and f1 times a jw t, right, plus f2 blah blah blah, and also fk times e over jw kt, right, plus blah blah blah, and at the final value n minus 1, this is the our last index in here, and e minus jw n minus 1 t. Okay, and so this can be organized as a one equation with the what? This is a simple summation of the discrete values, right? And so we can use the summation operator in here, just like this one. And so k is beginning with 1, right? And after that n minus 1 up to n minus 1, right? And so the fk times e over minus jw kt is our general form for the what? For the continuous to discrete signal. This is the 0 because the f0 does not contain the what? The frequency pattern, because this is coming from the what? With the 1 coefficients. I will explain that. What the reason to what? To beginning with the k is equal to the 1 value in the matrix theory. Okay? And so we can define the R general pattern in here based on this nomination. Okay, and so what is the discrete Fourier transform? Discrete Fourier transform is the what is taking the sample from the continuous Fourier transform at the some periods which is chosen in your systems. Okay, and so if I write the correct form of these terms, we should write it. The theorem can be given by the what the signal is periodic periodic at n, and so therefore we can rewrite the form as the what. Just now the k is beginning with the 0 but with basic difference. F n, which is equals to the what, k is equal to the 0 n minus 1, and f k times e minus j 2 pi, but n divided by n. This is the normalization of these values. Okay, and so we can multiply with the k. This is called to the what? To do discrete Fourier transform. Okay, these are the basic theorem for the what? For DFT definition. Okay, and so if we normalize the R signal in here with the basic periods, and then we can take the first value, but otherwise we cannot do that because in the first signal we cannot apply the normalization or the sampling ratio. For example, if you take the 1000 data to be sampled from a signal, maybe you may get the 50 Hertz frequency, but if you are continue to sample this signal up to 10,000, maybe this value can be changed, just like this one. And so we need to normalize the R signal or the R basis based on this information. But the graphical representation should tell us to what? To this difference. With the what? With the Euler identity shape. Okay? I will explain it in here. And so we can say that this summation is the what? Is the sampling rate with the what? With the Dirac delta function applied on this signal. Okay, and so we just use the what? The continuous Fourier transform, but with basic difference, which is the Dirac delta application on this signal. In the discrete time or the real-time operation for the embedded systems, for example, we should use this operation. Just remember that the Dirac delta goes to the what in the continuous domain to the infinity at the magnitudes. But in the discrete domain, we just have the what? The magnitude is equals to the 1 at 1 point, right? And so if we have the 1 point, and so we can transform the measured signal to the what? To the real time or the embedded systems. But in this case, we can apply the sum filter or the sum discrete convolution operation to what? To get the frequency of these terms. Okay, and so this summation can be represented with the what? With basic matrix. Okay, the upper summation can be expressed with the x is equals to w is the discrete Fourier transform matrix, and the x is the input. Okay, this is the input signal at the sampling rate. This is the DFT matrices. This is the what? The frequency components. Okay, but in discrete domain. And so how can we write the V in here. The W is equals to the what? In the first case, we have the what? The W in here. But what is the values of this W? W is represented with the what? E minus J divided by 2 pi K N divided by greater N. Okay? This is the basic pattern to build for the what? The discrete Fourier transform. Okay? Where is it coming from? It's coming from this one, right? Right? But just remember that if you take the n is equals to the 1000s or 10 is equals to 100, this DFT matrix is changed. You should know that. Okay? Because the DFT is applied or utilized on the whole signal in here. For example, if you have the 100 data, you must create the 100 times 100 matrices in here. Or if you have the 10,000 data, and so you must apply the 10,000 times 10,000 dimension of the matrices in here. You should create it. And after that, how can we represent this signal in terms of the matrix domain? In this case, we should know that the n is the 1 in this, and the k is the another in this, right? And so, if we use the fn is equals to the 0, we must search the whole data, just like this one. For example, we can take the some values and some values. We just pick the 0 value, and 0 value is what is utilized on or processed with the whole data. And so 1, this 1 process the whole data. 2 process the whole data. 3 process the whole data in here. Okay? Because the k is starting with the 0 up to what? N minus 1. Okay? And so this W operator possesses the k dot n terms in here. N is the what? Signal. For example, you can take the 100 value x, 100 times x value is processed, and so the dimension of the measured signal is the what is determines n. Okay? And so k is the what is another dimension of these terms, which equals also the 100. Okay? So in the first place, this WKN is collected with the what? The W over 0. Because we have the x value in here, just like this one, x0, x1, and x2, and xn, right? We have the input matrix. And so at each case, we should create the what? The 0 term in here, because the k beginning with the 0, right? And so these raw values collects the whole data to the what? To calculate the first values of these terms. Okay? You understand that? Did you understand? In the matrix form, just remember that the Fn in this signal, but this Fn creates the what? The one pattern, one data for a given 100 data. But in matrix domain, x0 or the f0 must be calculated. f1, f2, blah blah, fn must be calculated. For the what? For the whole the k is equal to the 0 to the n minus 1. And so, in the second case, we have the w0 is again in here, but with the some basic pattern, w1, w2, and wn minus 1 in here. Okay? Because at each case, we take to what? The x0s. w0, w1, w2, blah blah blah. And in each case, w0, w2, w4, and blah blah blah, and 2n minus 1. But why? Because the n is the what? Is 2 right now, right? And so at each case 2 times multiplication. And so in the fourth case W0, and so what's the over term in here? 3. And what is the over term in here? 6. And blah blah 3 minus 1, right? And so at the last case we have the W0 and Wn minus 1, W2n minus 1, and after all W over n minus 1, n minus 1. Okay? So this is what? This is our discrete Fourier transform. Okay? And so in real time application, if you have any pattern, it's coming from the what? The signal. For example, if you take the 10 samples from the embedded system or the real-time system, you must create the 10 times 10 matrices in here, just like this one. And after that, you must multiply these W matrices with the what? With the input value, measured value. And then you may have the what? The correct frequency values of these terms in here. Okay? And so this W matrix must be equals to the what? The n times n, right? This is the R basic generation for the what? For our algorithms. Okay? Any question?
We don't have a single number describe the frequency. We have n multiplied by n. How to manage this? How to understand the frequency from n multiplied by n?
Yes, that's a good question. In order to understand your frequency pattern, you should know that you must have the sampling period in your system. What is the sampling period? For example, if you are using the STM microcontroller, and then if you are using the ADC values or ADC components, and so this ADC is programmed with the what? With the taking the 1000 data at 1 second. And so what is the meaning of this? If you are using the sampling rate at the 1000, and so based on the Nyquist criteria, you possess the 500 Hertz frequency components in here, just like this one. Okay? And so if you have this matrix in here, and also you know that the Fs with the 1000 Hertz, and then you can scale the whole algorithm based on this information. For example, if you have the n pattern in here, but you may have the discrete time signal, and so just remember the continuous Fourier transform. If you have the 500 Hertz, this n is equals to this one or the last number, and so you can say that we have the 500 Hertz data in here. This matrix multiplication produce to what? These generations in here. Okay? In the next example, I can explain detailed in here this property, but in the real-time applications you must choose the sampling rate, and so this sampling rate divided by the 2, you have the maximum frequency pattern in here, and so this matrix can be applied to this frequency, and then you can scale the what? The whole region based on these informations. Okay? But we can write these examples in here. Suppose that we have 4 points, like X is the input matrix, input vector 1, 0, 0, and 0. What's the meaning of this? Which signal is that? Direct, but the discrete impulse, right? Or discrete delta function. And so, how can we create the W matrix in here? First of all, the n must be equals to the 4, right? This is known. And so, we know that the n must be include 0, 1, 2, and 3, right? These are the indices. And then, how can we write this signal in here? This is the greater W value. And so, first of all, exponential term must be given in here, minus j times 2 pi times, just remember n and k should be given in here, and 0 times 0 divided by 4, right? This is the first term. And the second term, minus j 2 pi, this is the 0 in this at the n, and so, but the k must be equals to the 1, right? And divided by 4. And also e over j 2 pi 0 2 divided by 4, and at the last term we have the j 2 pi 0 3 dot 4. Okay, and so this is the n, this is the k. Okay, this is n, this is the k. At the second part, we can write the e over j 2 pi, and now we should write 1, and so 0 divided by 4. E j 2 pi 1 and 1 times 1 divided by 4, right? E j 2 pi 1 2 divided by 4, and e j 2 pi okay 1 3 divided by 4, right? And so in the third case we have the j 2 pi times 2 0 4 e j 2 pi 2 1 4 e minus j 2 pi 2 times 2 4, and e over j 2 pi 2 3 4, and at the last case 2 pi 3 0 4 e j 2 pi, just tell me, 3 1 divided by 4, and e minus j 2 pi 3 2 4, and also e j 2 pi 3 3 4, right? This is what discrete Fourier matrices. Okay, but in a simple manner we can describe the whole terms in terms of the what, using the Euler identity. Can express these terms as the 1 minus 1 I minus I, right? What's the values of this term? 1. What's the values of this term? 1 1. Okay, and so this matrix can be represented with the what? The 1 1 1 1 1 1 1 1, right? What's the values of this term? 1 1 1, right? These are the numbers. And so what's the values of this term? Yes, and so which means that this is the pi divided by 2, which is equals to the what? I, right? E pi divided by 2, which is equals to the what? from the early analysis, I. And so, what's the double time of these terms? Pi. Because this is the E over pi 2. Yes, minus 1. And so, what's the value of the third time? And so, minus I, right? And so, what's the values of this term? This is the pi. Yes, minus 1. And so, this is 1 and this is minus 1, right? And so, at the last case, we have the minus I, right? And also minus 1 and also I, right? And so, what is the values of the multiplication of these two matrices? We have the x this time in here, and so this is the R representation, x, and so if you multiply these values with this one, and so what do we have? In the first term, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0, 1, 0, 0, 0. Okay, 1, 1, 1, 1. What's the meaning of this? What's the meaning of this? But you should understand that. What is that? What's the type of this thing? Yes, yes, it's a frequency, right? Okay. So, F and magnitude, and so we have always these terms. What does it tell us here? In a normal case, for example, if we apply the cosinus signal, and so we have the 1 Dirac delta function, but in this case, we don't have 1. What's the meaning of this? We contains the whole the frequency values. At this case. Why? Yes. And so, this could be interpreted as the what? We contains the whole the frequency pattern. Because the impulse response returns us to the what? The impulse response. Why do we need to use the impulse response from the system dynamic or the control theory or the signal processing? Yes, the impulse response tells us to what and what is the system. And so if I put or apply the impulse response to this W DFT matrices, and so we get the one value at each to what? DFT transformation, which means that we contains the whole the frequency patterns in here. Which means that the Euler identity possessed what? Every frequency patterns. Right? This is why we get the whole the one value in here. We have the 1 Hertz, 2 Hertz, 2 Hertz, and blah blah blah. Either if we apply the cosinus signal, we have maybe f equals 5 Hertz Dirac delta function in here. Do you get that, Baran? Just now? Okay. So let's take a break and then we will continue with the with the geometrical representation of these terms, okay?